Hey guys, my name is Lucas. I will be showing you guys today how to make a next word predictor. We'll be using TensorFlow. Um, we start with this Jupyter notebook, but the starting point here is already a Docker container launched from the TensorFlow GPU image. There's more information in how to launch that and how to set up that environment on the GitHub repository that's going to be linked in the description of this video. Um, so basically, what we'll try to do is create some deep learning models that will try to predict the next words in a sentence, and I'm gonna tailor this model to work with haiku poems. So they're basically little poems that are 3 lines long, and they usually speak about nature and stuff. I'm gonna show you guys in just a second some examples. Okay, so for this tutorial, I will be using, like I said, the TensorFlow GPU image, and using the GPU makes the training steps much faster. I was spending like 3 minutes for each epoch. And then on the CPU, then when I went for the GPU, this came down to like 30 seconds. Okay. So like I said, we're going to be using TensorFlow. The data set can be found at Kaggle in this link, and it's a data set of haiku poems. Okay. The first step is to read the CSV. Nothing special here, just a normal default separator, semicolon, just a comma separator. Okay. So the first thing that I explored was that I saw that in this data set, there's a few sources for the haiku poems. Some of them have much more poems than the other. But I kind of analyzed them qualitatively, in a qualitative way, and I saw that these sources were a little bit better for the purposes of this project. So I just filtered them out, okay? So the haiku poems, like I said, they're little poems, 3 lines long. For example, a tiny world unfolds and thrives, summer rain, okay? Um, and what we'll do is that this is going to be our training data set. Of course, we're going to parse it some more. And then we're going to try to use this to predict the end of other haiku poems, okay? So at this moment, the data set is the data frame has 3 columns, 0, 1, and 2, and the source. We're going to do some basic parsing here. So the first thing to do is I'm gonna create a complete column, which is nothing more than just summing these 3 columns, the 3 lines. For the purposes of our training, they're gonna have to be together. And I'm also applying some basic formatting here, putting everybody as a string. For some reason, there were some columns that were afloat. In the poem, there was a float number. And I also am lowercasing each one of the characters within the string, okay? So we drop any null values in any of the columns, and we also drop some duplicates. And for now, we have a reasonably sized data set, around 13,000 samples, okay? So the next step is a cleaning step. So I defined this cleaning function, which is basically gonna remove punctuation and numbers, okay? So I'll just make again the complete column, this time applying the clean text. And we'll notice that, for example, these question marks here, they disappear, and any number or punctuation would also disappear. Okay. So just some basic exploration on the data set. So this cell counts out the occurrences of each word. So of course, in the top here, and the most frequent word is the, a, of, and. But then we have some more interesting words: moon, rain, summer, spring. So a lot of stuff, leaves, sky, a lot of stuff related to nature, as is expected for this type of data set, for this type of poetry, right? So what's pretty cool about dealing with next word prediction is that one of the strategies that can be used is to create anagrams. Anagrams. So what is this? So basically, each of the poems we are going to always, so for creating the X and the Y for the training set, we're basically going to fetch sequences of n words, and then the next word is gonna be, so that's gonna be the X value, and the next word is going to be the Y value. Okay, so let me give you an example. So for example, for this, so these are the, so basically the first step is to just tokenize each of these poems. Tokenizing is just, in this case, for our purposes here, it just means separating the words. So we'll have many words. Okay, so these are what I'm calling our input sequences. Okay, and then our X value is basically going to be, so for example, fishing, and then the Y for this line is going to be boats, and then for the next line it's going to be fishing boats, and then the Y value for this line is going to be the following word, which is colors. So what is cool is that we'll have a line for each part of the sentence that we're in. So this will actually show the model, provide the model with examples of whatever position we are within the sentence. Okay, so this is a pretty cool strategy. Again, for exploration, I plotted out a histogram of the length of the size of our sequences. This is actually pretty important because the max length of the sequence is actually going to be pretty important for the size of our first layer inside of the model. But for our and what happens is that if we had like a maximum sequence of, let's say, 1,000, but then a mean distance of, let's say, 50 words, so and we use this max distance as the size of our embedding in our actual model, we would need to do a lot of padding, put a lot of zeros in there, so all the sequences can have the same maximum size, which would be 1,000, and this could compromise the model. But for our case, the sequence value is pretty reasonable, so the maximum value is 85, and we're just gonna work, and it's not so far from the medium value here, so we're just gonna work with the 85 as our maximum length and as our maximum sequence length. Okay, so this cell here just does another cleaning. It was just that I observed that for some reason, some sentences end with some blank white spaces, sometimes two white spaces together, and I just filtered out. I was working before with a maximum length of 100, but it's not even going to be necessary because this time it's going to be 85, the maximum length. There's not going to be anything bigger than that. Okay. So from that original X and Y, we obtained this curated X and curated Y, which is just a more cleaned out and parsed version of our actual X and Y data. Okay, so now we're kind of getting more inside of the actual model part, and the first step that we need to do is to encode our Y labels, and we're gonna do one hot encoding on that. But the first step here, just so we can have a map as after, so that when we make our predictions, we can know what we're predicting. So this is just basically a dictionary that just points out the index and the respective word for that index. And this inverse dictionary is just so it can be easier for us to retrieve the word from the index. And later on, we're going to see why it's useful, okay? So for the purpose of using the models that we train in another scenario and not only on this Jupyter notebook, I'm also saving this dictionary as a JSON file locally. So let's say if we put this model into an inference container, we could just access this JSON file and make the predictions and consult the index from there. Okay, so basically we're going to be trying to predict 11,595 words, and that's something that's pretty different from this next word prediction problem to other text classification problems, because in text classification you're most likely going to have much fewer classes to predict, but for next word prediction we'll basically be able to predict any other word inside a sequence. So we have many more options for the y value, and that's what makes it more challenging, but also more intriguing. And we see that, I don't know, this kind of enhances like creativity because we can predict so many different outcomes. Okay, so this function basically is to create the one hot encode for the y values. And the one hot encode, I don't know if everybody's familiar. So basically, each word is gonna be, we're gonna have a big matrix of zeros, and unless for the words themselves, which are gonna be assigned their respective indexes here from our label map. Okay, so yeah, so now getting into the actual training phase, the first step is for us to process our x values, and for this we're going to use a layer from TensorFlow, which is the text vectorization layer. It just makes it much easier for us to pre-process the x values. So basically, when I set it up here, I'm just saying that each x value is gonna come out as an integer, so as a number, and in this part, it's important to define the max length. And so for when we pad this, we're gonna pad based on the maximum length of that we predefined, and in our case is 85. Okay, and when we run adapt in the text vectorization, what we do is that we basically, and what we input to it is the created x values, and that's basically gonna feed all of the words that are available in our dictionary. Okay, and we need to make this layer output integers, because we're going to be working with embedding as our first layer in our models. And the embedding is basically going to be vectors, integer values, vectors of integer values, and the relationships between the relationships between the different positions of inside the embedding actually describes some semantic meanings between the words inside it. We can get back to that in another video. Okay, so this step here, we're basically dividing the data set into we're getting our x and our y, and we're actually transforming that into a data set that TensorFlow can use. And in this step, we also define our batch size, which is going to be important because we can't define a super big batch size because we would be our computer memory, video memory wouldn't support it. But if we define a batch size that is too small, the model would take forever to train. Okay. And we also need to shuffle the data set. So this is basically to feed the samples randomly to each batch. And this shuffle part is actually pretty important because if we put a value here that is too smaller than the actual size of the data set, we will be losing a lot of information, and that has happened to me before, and I was and when I was training, the accuracy was stuck, and the accuracy and the loss was stuck, and it took me a while to notice that it was actually because my batch here was very small. So for the purposes of this data set, the data set's quite small, and it's perfectly fine to work with the complete size of the data set. Okay, so we're just basically going to shuffle it, each one of the samples inside it, and then distribute them in the batches of this size. Okay, this step is just to validate how our data set looks like. This is actually a pretty good this has pretty good debugging information, because what can happen is for us to not notice stuff like trying to predict more classes than we actually have. So that was a problem that I fell in once. Okay. So now for the training itself, I'm gonna do the training using two architectures. It's going to be the LSTM, which stands for long short term memory, which is a type of recurrent neural network. So basically, this LSTM, it's an architecture that is appropriate for sequences because it considers the whole sequence. It considers a little bit of the past words, and it has like forgetting mechanisms and stuff. So this is suitable for this type of problem. And later down, we're gonna be and further down, we're gonna be dealing with the transformers architecture, and the transformers architecture has the advantage of finding semantic relationships between the words together. So it has more context awareness, and we're gonna try to use it and see how each one performs in predicting the next word. Okay. A few stuff here. So the first step is, like I said, is using an embedding layer to try to retrieve and to establish the semantic meaning between the words within the sentence, right? And then we do the LSTM layer in a bidirectional manner, so it goes back and forth. And the last layer is a dense layer with the size of the amount of classes that we have in our problem, so that we can have the opportunity to guess, so the model can put its the probability for each one of the words in our word universe here. Okay. So another cool thing here is this early stop monitor callback. So what basically it's going to do is that it's going to monitor the loss function as the epochs go on, and if it does not improve, which is in this case is to drop for 2 consecutive epochs, then the model is going to stop, no matter which epoch it's in. Okay. Because we're dealing with a multi-class problem, we're going to be using the softmax function, so we can have a probability for each word. As for the loss, we'll be using the categorical cross entropy, and for the optimizer, we'll be using atom. I actually see here that I set atom here and I set the optimizer here with the learning rate. So this learning rate is going to be ignored here because the other way would be to put the optimizer over here, but that's okay. But I don't recall what's the default value for learning rate for TensorFlow, but I'm pretty sure it's not far away from this one, if it's not this one. So the training, I set it to run for 20 epochs, but with the early stopping monitor callback. And what happened, so let's go here to the beginning. So the accuracy kept going up, and it didn't actually reach the 200 epochs because before the early stopping monitor callback made it stop, and we reached this accuracy. This accuracy actually doesn't mean very much. I mean, because the best way to evaluate this type of model is in a qualitative way. Okay. So these are just plots for the loss function and the accuracy as the epochs go on. So what this basically shows is that we actually reached the point that the model is stable and it wouldn't improve anymore if we let the epochs go on indefinitely. Okay. Now this step here is quite important because it basically makes the model ready for a production scenario. So basically what we're doing here is attaching the text vectorization, which has all that information and how to map the different inputs into integers for this model, and to feed it to the model itself. And so what we're doing is we're attaching this layer to the final model. And so what this does is that it allows that for when we save this model and then we open it somewhere else, like in a runtime inference container, like in production, not only in this Jupyter notebook, we can just load this model the way it is. And when we go back to that training JSON, that map, that label map that we saved as a JSON, if we have this model and that file, we'll be able to make predictions with this model and actually map out to the words that it was trained on. Okay. And as we can see here, when we ask the TensorFlow to make a summary of our model, we actually have the input layer, and then we have these inputs being fed to the text vectorization layer, which is going to do the conversions in a way that's adapted to the data that was fed to this problem. And then the output of the text vectorization layer will be fed into the model itself. Okay. So now let's test the LSTM model. And what we'll see here is that we're kind of simulating a production environment, so we're loading the label dict again, and we're also loading the model that we just trained. So at this point, we lost that model that's in memory, okay, and we're using the model that's on disk. And this is cool because we're already making sure that this is going to work in any other scenario, and not only with whatever is in memory right now in this section of the session of the notebook. Okay, so what's basically going to happen here is that I have a few C text, and the C text is basically the text that my model is going to read and then predict the next words. Okay.